I wanted to start off by talking a little bit about the exam, just reviewed some of the questions and make sure everybody gets the points that they need, because I guess there were three things that I wanted to fix on the test, and so if you happen to get any of these questions, I guess just let me know. Right. Oh yeah, other thing, I realized after last lecture, or like the review, I guess my audio is messed up, so I apologize if anybody is talking. I know that's not normally. I know a lot of people use voice chat, but just in case, I'm sorry if I ignored you. Right, anyways, there are three questions that I think we needed to look at, and so if you got any of these, just send me a message, and I will fix it for you if I haven't already. I think I got everybody, but, there's always a chance that I haven't. So the first one was this one, where it was every recursive function has this many cases, this many base cases, and this many general cases. And we never really talked about the term general case, although we have been using it. It's just another word for a recursive call, and that's just more like the mathematics term, because generally when you use recursion in math, it has to be a function, and a function in math is a little bit different than a function in C++. So I typically don't use that term as much as I just say it's a recursive call. So a general case, right, if I had like Fibonacci sequence, or not Fibonacci, factorial, then remember, right, what we did in order to figure out the function call was we wrote it as something like n factorial is equal to n minus 1 factorial times n. I mean, we did it the other way around, but this is the same, right? So this is a general case. And so when you write the actual function call, some people will call that a general case when we do something like, fib n minus 1 times n. Some people will call that, instead of a recursive call, we'll just call that the general case, which I guess it isn't an expression, and it's not just a call exclusively, but it's called that in math because you can write it in terms of a specific variable. But that's not always the case when we're solving problems recursively in computer science, which is why I don't usually use that term. So I'm throwing specifically the second part of this question out. So everybody who missed the second part, just let me know and I'll give you the points back on that. I think I got everybody. It wasn't a whole lot of people. Second one was this virtual inheritance one. So what is virtual inheritance? I think over half of you got this question. And it actually doesn't have to do so much with virtual functions as it does with a special type of inheritance that we didn't talk about. So if you got this question, let me know too. I'll give you the points back for it. I guess it just kind of slipped through. There were a lot of questions. There were like 130, and I think I missed a couple of them in terms of like pruning it if we didn't go over it. So virtual inheritance is actually like a special type of inheritance that specifically deals with inheriting from multiple classes. So we never really talked about that, but it really is a thing in C++. So, and pretty much any language, it's just not very commonly used, and I think most other languages require it to be a thing called an interface in order for it to work. So let's just say we had like a parent class, like game object, like we've been doing a lot, and then on top of that we'll say that we have maybe, so it would have to be pretty generic, but we'll just keep going with this. So we'll say maybe player has some stuff, and then maybe we have a generic class here for enemy types. And then, for some reason, I want to make a class that is both a player and an enemy. So it borrows both of the functions from a player and an enemy, and for some reason needs to have both of those common things. So what I can actually do is condense both of these back and inherit from both of them. So maybe I can say this is a a player enemy or something like that, where it has to inherit from both of them. And so that's not something that we've covered so far, but it is always an option to use, is to inherit from multiple places. And a lot of people will call this diamond inheritance, because the shape it makes is a diamond. And it means that we're inheriting from two different parents, and both of them come from the same tree. And so an issue that we might have with that, and this is where this virtual inheritance comes into play, is I might have a virtual function here. So we'll just say virtual void like update, so we'll just say up. And what we know about virtual functions, right, is that you can override it. So if I say I need everything to implement this, and then I write up and it does something here, and then I write a different update in this class, then when I go to inherit here, right, what happens when you inherit is it goes and it takes everything from the parent class, the base class, right, and it borrows all of the member functions and the member data, right, so you can use any of those in the class that you're inheriting from. Now the problem here is if we go and inherit from two classes, there's nothing inherently wrong, for lack of a better word, with inheriting from multiple classes, but we end up encountering a problem if they share variables and or functions. So if they share some sort of data where they use the same identifier, that is the name that they're using. So if I try to inherit update from player and update from enemy, those both have the same name, which means when we go to inherit here, and we inherit from both of these, then it's going to say, well, do I want update from here, or do I want it from there? And so virtual inheritance in C++ is just, I actually don't remember the syntax, is specifying which one of these that you want. So you can use virtual inheritance to say, well, I only want this one. And then we can throw that one out. Right, so yeah, it's a way to fix a problem if you have duplicates when inheriting. And I guess just since I did mention it, the syntax, if you ever want to inherit from multiple classes, so if I was to make class player enemy, something like that, the syntax for inheriting from multiple classes is basically just the same syntax for inheriting that we're used to. So let's say if I wanted to inherit from player, it would just be that normally, right? And then the way you inherit from multiple is you put a comma, and then you just keep going. So I can inherit from enemy, and that should be valid in C++. So if you ever want to inherit from multiple, you always do have the option, but I think it's very niche, and that's why I didn't really mention it. Yeah, sorry. So I guess I blanked on that one when I was removing all the things. So it ended up in the test. But that's what virtual inheritance is. It's basically just if we have multiple, pick one that removes the duplicate. Right. So if you got this question about virtual inheritance, which most of you did, just make sure I gave you the points back for it, all 5 of them. If not, let me know, and I'll give that back to you. And then the last one was, this one had an issue. So it, yeah, for some reason it just said like no answer text provided as one of the answers. So which explains the advantages of using a linked list, and then you're supposed to select all that apply. So if you got that one, again, let me know. It looks like only 6 of you got it. I'm just going to give you the points back that it took off if you didn't put the ones where it said like no answer text provided, and then one of them also cut off here, I think. Whereas, yeah, this one, insertion of new data does not require the, and it just cut off. So I think maybe just hit the add button too many times when writing the question, and it just threw that in there. Right, so if you got any of those, just let me know, and if you think the points are wrong, Or if you look over the test and you think maybe there was an issue with the grading, let me know as well. Right, before I start going over any of the other questions on the test, did anybody have any questions regarding any of the topics on it that you wanted to go over? And it's okay if you don't remember the exact full question, but if there's any specific topic that you wanted to talk a little bit more about first. The recursive parts? Anything in particular about it? Or just, I probably have a recursive one somewhere. If not, we can go over maybe one of the major ones, unless you have a specific example. I actually don't, I guess, have a recursive one downloaded. Let me go to Web Campus. But yeah, if you have a specific one, let me know. Actually, I suppose. Here. Programming question using insert lookup. Oh, like the last question for the linked list? Statistics. Yeah, okay. Yeah, we can take a look at that one too. Let me see if there's any specific recursion ones that would be good to go over. If not, again, if you remember any specific ones, either put it in the chat or you can always ask later and send me an email or a Discord message and we can go over it. Maybe this one. These aren't very well organized, I guess. This one, link list. Well, this is the only one I see that I think most people missed. Let's take a screenshot of that really quick. Okay. I'll grab the linked list one if we have time. Oh wait, sorry, I meant the question to print out a recursion without using a list. Or without using a loop. Did you mean, so the one I found was the print reverse one, was there a different one? Or did you mean the question where it was can we do recursion, or do we need a loop for everything? And and add all the array value. Okay, never mind, I know which one you're talking about. It's just a matter of finding that question. And if I can't find it, I remember which one you're talking about, so I can at least describe it. Oh, here it is, I think. Count print 2, this one does multiplication. Yeah, okay, I found it. Yeah, we'll talk about that one. Okay, here we go. So let's just remove that then. Then we'll go to a new page. Recursion. Okay, so let's write this function that's described here. So it's a recursive function called countPrint that takes an array and the size of that array, and then it does two things. It prints it in reverse, and then it also finds the sum of the thing. So let's worry about the sum first, and then we'll worry about the printing part. And so something to note is it actually doesn't matter which order we do the addition in, right? Because whether I do 5 plus 2 plus 1 plus 4, or 4 plus 1 plus 2 plus 5, it doesn't really matter, right? Because either way, I'm still going to get the same sum. And so the only difference if I went this way, 5, 2, 1, 4, and 4, 1, 2, 5, is that it would be like head recursion versus tail recursion. And the only reason I bring that up is because we're going to have to worry about the order later. But since that's not something that we have to really worry about as far as the addition goes, we can just kind of write the addition and then insert the print later. So we know it's int count print, and it takes a integer array called r, and it also takes a size of the array. Right. So for recursion, we always need those two things, right? We need a base case, and then we need some sort of reduction operation along with a recursive call. So let's address the base case first. So the base case, I would say, is when we're out of numbers to add. So if the array is of size 0 or size 1, either one is an okay base case, then we know we're done. So I'm going to be, I guess, more proactive and do the size equals 1. That way we save one call, I guess. So if we have one element left, then what we know is we need to, maybe I should move this down, just because I know we're going to write the print later. But, so if size is 1, then this would be our base case, right? And when you have an array of size 1, then the only thing we need to worry about is actually returning the value in the array at that position, right? So at that point, if I asked you to take the sum of an array that only has one thing in it, the sum of that is just the thing that's in that array, right? So if I had just, versus if I had something like this, where if I asked you to take the sum of that, you'd have to add 3 and 6. If I asked you to take the sum of a list that just contains one thing, then it is just that one thing, right? By definition. So our base case here is if we have an array of size 1, then the sum of that array is just the thing in that array. Maybe I'll erase this so it looks nicer in the picture later. But that's the general idea of where we got this base case from. Is by definition if you have one thing that its sum is just itself. And if I did size 0, then I would say that the sum of an array that contains nothing is 0 by definition. Right, so that's our base case, and then the other thing we need is a reduction operation along with a call to the function itself. So we know what we want to do is add a value to what would happen if we went and added the next one. So since it's a value returning function, we'll just return it immediately. And what we need to do is return the current value in the list, which would be, so if the array is size long, then I think it makes the most sense to add the thing at the end. So in the first thing, I'd say we'll add 4, and then 1, and then 2, and then 5. So I know I said it doesn't really matter which order we call it in, or sorry, which order we add it in, but I think it would make more sense to do it backwards here. So what we'll do is we'll then add the array that's at, or sorry, the integer that's in the array at position size, not +1, size -1, since that would be the last thing in the list, right? If it's size long, then -1 is always the last thing because we start counting at 0. And then I need to do addition between that and the next thing in the list, which was the next case, right? So we will need to do plus count print, and then we need to pass the array, and we need to reduce, so the size is going to decrease by 1. Right, so this right here is the reduction operation, and this whole line is our recursive call. And just to go over what this says, right? It says take the last character, or sorry, not last character, last integer in the array of the current size, and add it to the sum that I would get from adding the array that's 1 smaller. So if I think about that here on the first case, what I would be saying is take 4 and compare its sum, or add its sum to the sum of this array, 5, 2, 1. Because if we think about it, 5 plus 2 plus 1, if I add that to 4, it will give me the sum of the whole thing. And then on the next call, right, it will say, okay, the next thing is 1. And then what I need to do is add 1 to the sum of everything before it, which is 5 and 2. And then on the next call, we would say, okay, add 2 to the sum of everything else, which is 5. And we will go and call it on that. And then once we get to 5, that's the base case, right? It'll say, well, okay, this is an array of size 1. By definition, I can actually add that together because I know how to add something that's 1. Right, so it'll work its way backwards until it hits that base case. So it starts here, passes this list, and tells it to find the sum of that. Takes this and adds it to the sum of the list before it, and then keeps going. Right, so that should take care of the sum part, and then we need to actually do the print. And I think we always want to print in this case, right? Because we only stop once we hit the base case of 1, and we want to print still if we have a list of 1. Because that's still an element in the list, right? So all we got to do is just say cout, and then I'd say it would be a good idea to print the thing at the end of the list. So we'll just say size minus 1. And so if we always print the thing at the end, and we're working our way backwards, then we'll print it backwards, right? So on the first call, 4 is at the end, and then 1 would be at the end, and then 2, and then 5, and that would be it backwards. And then, I don't know, maybe we'll just put a space to make it look nice. I think that should be it. So, when you have a problem like this, I think it's a good idea to kind of break it up into the components. So we have multiple things that we need to do here, right? We needed to add and then print. So, maybe tackle the adding case first, and we need to think about, how do we recursively do this? Well, the sum of a total list would be the last thing plus the sum of the list to the left of it, and that works recursively, right? Because we're reducing the size of the list and using a previous solution in the thing, right? In the order of cases that we would write. Any questions on that? That should be okay, I would think. For the code, at least. It doesn't really fit on screen. That's a bit of a problem. Maybe that's a little better. I don't know. And also, any other questions anybody wanted to go over on the test? I'll probably try to go through them really quickly. I don't want to spend too much time. Unless anybody specifically wants to go over stuff. Right. Let's go over maybe 2 more very quickly. And yeah. Oh, palindrome question? Yeah. Actually, that one was kind of challenging if you haven't seen it before. Let's see. I do think out of the programming questions, I think that was probably the most difficult. I don't know how well everybody did on it. I don't even think I need to copy and paste that. We can explain it. So a palindrome, right, is just a string that's the same forward and backwards. So the example it gives in this one is race car. So this is a palindrome because everything is symmetrical, right? So if I split this down the middle, E is equal to itself. The C and the C here are both the same. The A and the A here are both the same. And the R and the R are both the same. So palindrome is just like a word that reads the same forward and backwards. And one thing we should note about that is that there's two kinds of cases for this. So there's one where it has an odd number of letters, like race car. So the thing to note about that is that it is it's like split or symmetrical on a single letter, and so the E kind of reflects back on itself, right? And then we have another case where we could have an even amount of letters. So if anybody can think of a word, let me know. That has an even number of letters and is a palindrome. Noon, right, would be... That's a palindrome with an even number of letters, so the symmetry is right there, right? Then there's an O on both sides and a N on both sides. The only reason I mention this is because I think some people got really close to the answer and then just didn't consider that fact and had it break specifically on this one, on even cases. Right, so what we want to do is write a function called isPalindrome. Maybe I'll just call it isP for the sake of making my writing shorter. And it takes the string that we're checking. It takes a integer, we'll just call it I1, and an integer I2, and these represent the indices that we are checking in the array. Right, so what the question said was we need to tell if a given string is a palindrome, and we also need to assume that the initial call for this function is with I1 being 0, so in other words it's starting here, and I2 being length minus 1, so that would be there. That's not very helpful. L and 1 kind of look the same. Length minus 1 would be the last character, right? And so the idea with this is that if we check both ends of it, since it is symmetric, we can kind of like pincer our way to the middle, and if we keep checking the characters that are symmetrical on both sides, and they keep being the same, then we know that it is a palindrome. And if we ever encounter any that don't match, then it's not a palindrome. Right, so there might be a better way to write this, but the first way I would think to do it is just immediately check if string sub I1 is not equal to string sub I2. So in other words, if the characters don't match, then we know it's not a palindrome, right? So if I said something like hello, then the first two characters I would check would be O and H, and those aren't equal, and hello is obviously not a palindrome, right? So, so I would need to say, well, it's not a palindrome if they don't match on both sides. So I could say return false if that's the case. And then otherwise, we need to do something else. So, actually, I should probably check for something else before that. So that is one thing that we need to check. I'm going to move that downwards. What we should check maybe before that is the base case. So a base case would be if we've gotten to a position where we've hit this symmetrical part, right? This blue and green line there. So either what we've had happen is that the indices, so as we go along, right, hopefully our idea here is that the index checking the last one's going to move left, and the one checking the left one's going to move right until they meet at the middle. And so something on this one, they would meet at the middle when I1 and I2 are the same, which means that they match on that one, right? Alternatively, on this one, notice that we can't be done when we're here, when I1 and I2 are on the O, but when we actually do that, the next step, right, if I was checking this one, I2 is going to move over here, I1 is going to move over there, and we actually get a case where they're not the same as each other, right, if it's even, and I1 will end up going a little bit to the right of I2. So what I think is a good way to check this one is if I2 is less than or equal to I1. In other words, if we've either reached the center with the equal part, or it's less than and we've actually moved past it on an even case, then we know we're good. We can return true. So what this says, right, is if we've reached the middle or have gone past the middle and we never ended up finding a case where it didn't work, then we know that it must be a palindrome, because if it never failed, then it must be successful. Right, so that would be our base case, and that would be the return true part. And then the other part we said was else if str I1 does not equal str I2, then we can return false. I could actually probably throw this all into one function call if we wanted to be really efficient and fancy about it. And then else, so if we didn't find that they didn't match, so this one, right, was if the characters that we're checking, like this red and that red, or this green and that green, were actually equal to each other, then we have to keep checking. Because I could have a word that's like RATE, I'm just making up a word, but something like that, right, where it's the same on both sides for maybe the first two characters, and then in the middle it just breaks. So if we get that it is a palindrome so far, we're going to need to keep checking until we reach a base case. So what we'll need to do is then keep going, and so we'll return the result of going and doing the next step, which would be is palindrome, and we're going to call it with the same thing, so we need to pass it the same string that we've been checking on. And then I1 was the index that was keeping track of the left index here, and I2 was the one keeping track of the right one. So if we want to move towards the middle, we're going to need I1 to get bigger, I2 to get smaller. So I1 we can say plus plus I1 and plus plus I2. Okay, and that should take care of everything. So we have these two. So we actually have two reduction operators because we have two parameters to reduce on. So these are both reduction operators, and then this one is our base case, and this one was just a extra thing to break. This was like a break early. So if we never found a match, or if we found that it didn't match, then we could always stop early. Right. Any questions on that one? I do think that one was a little bit challenging if you haven't seen it before. At least I think that was like the most challenging out of the recursive ones, in my opinion, at least. Okay. I think there are two other ones. We'll just very quickly just take a look at them, and then we'll try to talk about some other stuff. Oh, and there, actually, I guess there was one other thing I'll mention in a moment. So we have this one, which was, I think, one that a lot of people got, which was the exception class is the superclass for all exceptions. Why is it useful to have a shared superclass among all exceptions? So we have that standard exception. I think everybody got that part. Right, that's the base exception class. And then we have a bunch of exceptions that inherit from it, and we can also inherit from it ourselves, right, if we wrote a custom class. So in that linked list example, I think I wrote something that was called like an out of bounds exception, and that was specifically just for linked list. So I had like a special custom exception that just applied to linked list. That way, if you had an exception, you could tell, well, it came from the linked list class. And there are a bunch of other ones, right? There's like the bad allocation and the length error and the big file error and all those other ones that you had in assignment 8. And they all inherit from a single exception class, right? So the reason we do that is so that we can catch them all. Much like a Pokemon, I guess. We want to catch all the exceptions. So if I do try and then I just do, some code that's unsafe and, might throw exceptions, then if I do just catch exception E, so if I catch the superclass of everything, which is the exception here, right? Everything inherits from this. Then whether I throw a length error or a bad alloc error or even a custom error like I did for my class called out of bounds, or whatever custom exception, some library that you might use for something specialized, throws, then you're going to be able to catch it no matter what, right? You don't even need to know anything about that class or anything about the type of error that was thrown. You can just catch exception, and it will do it because they're all versions of exception, right? They're all inherited from it. So if you ever want to just catch every single thing that is an exception, you can always just do exception E, and even then, if you were to continue the tree downwards and make maybe your own custom exception class and then have that branch off, then you could do the same thing with that. So the advantage to this, right, is if I have the exception class and I have bad alloc and length error and all of those things and a bunch of other stuff, then if any single one of these gets thrown, I can catch them all just by putting exception. And so I don't need to remember each specific exception that could possibly be thrown, and I don't need to know exactly what the exception being thrown is. Just if you think your code's not going to work, maybe that's a good idea to throw in there, and then you can figure out what the exception is later without having a program crash, if that makes sense. So the short answer to this, and the one I was looking for on the exam, was basically catch everything. So if you have a shared superclass, then you can catch every type of exception just by catching that exception class. Now the exception, pun not intended, the exception to that in C++ is the fact that you can throw integers and strings, so those don't get caught when you throw an exception, right? And you have to use that ... operator. Which, again, I'm not a huge fan of the fact that you're allowed to do that, but C++ supports it, so not everything is a type of exception that you can throw in just this specific language. So that would be that one, and then the other one, really quick, I wanted to go over. Oh, this one's really short, but a lot of people miss this, and I just thought it would be important to mention. So what are the two types of templates in C++? So that would be a class and a function. So we can make a template out of a class, and we can make a template out of a function. And that's really as simple as that. So just keep that in mind for later. Right. Any other quick questions? Oh, and actually, there's one thing. For the question that asks the code in main is valid. Oh, actually, good question. Yeah, I think one person got that right. So that was actually kind of a hard one. Yeah, fair question. Let me see if I can find it really quick. Yeah, here it is. Yeah, actually, that tricked a lot of people. It actually is valid code. I actually made sure and I went and compiled it, and it does run. There it is. Yeah, so the question you're asking about, I assume, is this one. Given a template list class, is the code in main valid? And if so, explain what the list variable is, and if not, explain what the error with it is. So we have here a template class called list. We don't really need to care too much about what it actually does, but it's just, kind of like a vector, really. So it dynamically allocates an array and keeps the size or something like that. But the important part here is that it keeps some array of a generic type t, so we could determine what type of data that the array holds by simply putting a type there when we declare it. So what we've done here is instantiate an instance of the list class, and we've done list float. And so this might seem strange at first because we're using a template class to make a template class, and that might seem like it's invalid at first, but it's actually totally not. And we can even imagine what the compiler would do here. So it's kind of going to recursively check this. So what the compiler is going to do, right, when it tries to make a template class, is it's going to see, well, I see that angle bracket, so I know this is a template class. I'm going to go try to generate the code for it. And that's what it does for a template, right? Is it, if I wrote, like vector int, then it's going to go into the library for vector, which contains a template class definition that somebody else has written for you, and it's going to say, okay, that type now is an integer, and it goes and replaces all the things. So if I have like a generic type t, it's just going to go and make the code where it replaces it with an integer, right? So what this will say here is, okay, well, I need to go make a list where the type of the thing is list float. And so that might seem a little strange at first because it's kind of recursively defining itself. And, maybe that's not allowed, but if we think about it, there's no list float type yet, but it can go and make it. So here, what it will do is it will say, okay, well, maybe I should finish parsing this whole thing first. So it will go and read this part and say, I want to make a list that is a list of floats. So what it will do first is, if we kind of imagine for a second, what it looks like, it will go and check this type first, and it will say, you want a list of floats? Okay, well, that's doable, right? Because all that means is that I need to go to the list class and replace all of those t's, the generic type, with float. So it will go and the compiler will generate all of the code where t here is just replaced with float. And now what happens is the list float class does exist. So I'm able to instantiate it. And then what it will go and do after that is it says, oh, well, you want a list where the type is list float. Now the code's been generated. There's a definition for a list float class where all the t's are replaced by float. So it exists and it's valid. So it will actually go and replace all of the t's and make a separate generation of code where all the t's are replaced by list float. And that's totally valid, right? I can have an array of classes, even if it is a template class. That's totally allowed. So what this does is actually makes a list of lists, and those lists contain floats. And that might, again, seem strange at first, but just to demonstrate that I'm not crazy and maybe you do have a practical use for this, imagine you're in 2D, 3D space, something like that, and you have points. Well, maybe it makes sense to have a list then of points where you have coordinates, and maybe they're not all of the same size. So what I can do is create a list of those numbers and then put those themselves in a list. So it's totally okay to have a list of lists, a vector of vectors, if you wanted to go with the C++ built-in class. Totally valid. You can put as many layers as you want on that. And the compiler is totally capable of generating it because it will go from the inside out recursively actually, and generate the template classes necessary to generate the things on the outside. Yeah, that's fair. A lot of people did miss that one. I didn't intend for that one to be that hard, but I think most people thought that was invalid. While I was doing that. But yeah, the code's totally fine. And in fact, I think this is useful. I think I'm writing assignment 11 right now, and I think I'm going to force you to use this. Anyways. Although you won't have to worry too much about all this technical stuff. Right. Any other questions? I think that's the last one I might talk about. I guess if you have any other questions, either put it in chat, or you can always ask me specifically if you have an individual question. Just send me an email or a message or something. So I wanted to just tie up some loose ends, I guess, before we talk about the last subject. And I'm going to try to fit that in as best as I can. I realize that we have another break next week, and then the week after that is study week, and I'm, technically not supposed to talk about new stuff during study week. Or at least that's the thing that they say, right? I don't think that's actually true. I think you're allowed to talk about new stuff during study week. I think everybody just gives that excuse. But we'll try our best not to do too much new during study week. But I wanted to at least tie up some loose ends if Sally would respond. Maybe we won't. Who knows? If Sally doesn't respond, there it did go. Okay, well, it disconnected. That's all right. Okay, I was going to say, if Sally went down during the 20, 30 minutes that we've been talking, that would be unfortunate. Right, so I think... I need to find out where this is. LS... Oh, whoops. That wasn't right. LS... what did I call it? I made a directory. Oh, I think it's the example one. So cd example. ls. Yeah, there we go. Alright, so what I wanted to talk about really quickly, maybe for just 5 minutes, was a Makefile. And so I have here a C++ program that I wrote when I took this class called harmonic.cxx, which is just another file extension for C++. And it's it's something that I would compile and run. And so what I've done is I've created something called a Makefile, and you specifically have to name it Makefile when you create it, and it contains this here. So it contains basically a line that says my program, which is the name of the executable that I want to make, and then the source file, and then what it contains is either one or multiple lines telling the program to compile. So if I was to compile this normally in the command line, I would probably do it something like this, right? G++. The /O is for output, so or object file, maybe. I think it's for output. It will output the executable with the name my program, and it will compile it from harmonic.cxx. So really, this is just things that I would normally type on the command line to actually compile, right? Is that line. Now, what the Makefile allows you to do is it allows you to run all of those without explicitly having to type them out. So what I can do here is if I type the word, whenever it responds, okay, there we go. If I type the word make, it will actually take that make file, and you'll see it runs that command from the file. Cool. And so if I ls now, you'll see that I do have an executable called my program, and I can assumedly run that, but I don't know if it still works or not, or whatever. and it does something, and I guess finds like a harmonic sum or whatever this program did. But the point here I'm trying to make is that if you wanted to, let's just say, compile a bunch of different things, and you're tired of typing in, this whole line every single time, you can throw it in a file called Makefile, and you'll be able to compile it like that. And so it might just seem strange that I'm bringing this up, and this isn't a very involved Makefile. It's kind of an art, and I'm not that great at it. But what a Makefile allows you to do is call multiple compilations. So I could keep doing more G++ lines after that if I wanted to compile multiple programs at the same time, and just basically type one word and it will compile it. And there's another advantage to it, which is part of where this syntax comes from. So what this does actually is it kind of automates the way that your compilation works, and it will only compile things that you haven't updated since the last time you compiled. So what the Makefile should do, kind of secretly, is keep track of the last time you modified a file when you went and compiled it, and then it will basically check, is the date newer? If so, recompile this thing. If not, leave it as is. And yeah, that's kind of the advantage of using it. So really, I don't think we'll ever have to nowadays keep your own Makefiles. So that's why I'm not going into a whole lot of detail about how to actually write it, and I'm not that great at it anyways. But I think it's important to keep these in mind, and at least I wanted to bring it up because you'll see that these are commonly used a lot, and it's something like Visual Studio. It kind of keeps one secretly for you and just runs it whenever you compile a big project. So there's a lot of places that still use Makefiles, but they're kind of hidden from you, and I thought that might be important to just bring up. It's an efficient way to compile all of your programs if you have multiple, and it's very useful for a big project. If you had like 100 programs or 100 source files that you had to compile, and you only updated one of them, you don't have to sit there and wait for 100 to compile. It will only compile the ones that it needs to. Right, that was just a random loose end I realized I hadn't talked about, and it wasn't on like the test or anything, but I realized this is usually a class where we talk about this, and I didn't see it in the syllabus, but I thought it would be important. Any questions on that? Again, you probably won't have to maintain it. Just know if you ever have a Makefile that the keyword is make, and it will make everything. I also bring this up because they usually have you do it in the compiler's course, and I at least want to make sure you've seen it at some point. Or not the compiler's course, the operating system course. Okay. Right, so there are two other minor things that I just wanted to address. One was very minor. I very briefly mentioned it before the exam, although we didn't do any examples of it. So I tried to remove almost everything about it from the exam questions that we got. So if I have a linked list like this, then the structure we've been saying is that the end always points to null, right? Is just to make the end never point to anything. And so a thing that we can also do instead of having it be null is we can have it point back to the beginning is another option you'll see people pick every once in a while. And in this case it's called a circular linked list because the beginning goes back to the end. Or sorry, the end goes back to the beginning. And the advantage of doing this is the fact that we only traverse linked lists in one order, right? If they're singularly linked at least. So this allows us to go back to the beginning if we, for some reason, need to. And really the only thing that's different about the code for this is that when we go to insert at the end, we'll probably need to keep track of where the end is, or we can just like arbitrarily insert at the beginning But the idea is we're going to have to update more pointers if this thing is not null. So if I was to go and insert, I would maybe have to keep track of where this is and where that is and kind of make this point around there. In some way you have to modify your insert wherever you decide to put the node. I don't know. Kind of depends on what you want to do. You have to keep track of some more things. But everything other than that is essentially the same. The lookup and the deletion are essentially exactly the same as the normal one. I think the insertion is the only special one. We just have to decide on something depending on how we decide to implement it. Any questions on that? Just something random to throw out, because I did notice there are a few questions about it before I removed them from the test. Okay. So let's start talking about the last thing that we got to talk about, and we'll try to get through as much of that as we can. In programming, there's a lot of scenarios where you might need to handle some sort of object and get them as they arrive. So let's just imagine that we're writing something to go with the metaphor that I think most people go with. Let's imagine that you're at like a deli or something, like a restaurant, and you have the counter, and then there's the cashier or service person helping you, and person A shows up, and then person B shows up, and then person C shows up. And so we want to write maybe a program, or at least just think about, well, how are we going to handle in what order these people are going to be able to go up and talk to the cashier and order their food. So if A shows up and then B shows up and then C shows up, who do you think gets to go first? Or like, what would be your like gut feeling? What do we think would be fair about that? So kind of make a line in front of the counter. Who gets to go first? Who gets to go second? Who gets to go third? If this person showed up, and then that person showed up, and then that person showed up. So I think if we want to be fair, right, then person A would go, and then person B would go, and then person C would go, right? So generally when you walk into a store, the first person who shows up gets to be the first in line, right? And everybody kind of just piles on to the end. So maybe if these people are here and ordering, and a person D walks in, then what we want to do is put them at the end of the line, right? Not just let this person cut in and be here now, right? And then make B and C have to wait longer, because everybody would be pretty upset at D, I would imagine. So I think the fair thing to do is to let everybody go in order, right? The order that they show up in, that is. So this inherent, at least I think so, common sense kind of way to approach things arriving and then handling them is to handle them in the order that they show up. And so when we do that, that's called a queue. And you might just make the parallel between that and a line at like a restaurant or whatever place you go to that has lines. The first person that shows up is the first person that gets served. And so another term you'll see for this is FIFO, which is the first that's in is the first that's out. So whoever shows up first is the first one that's going to be out of this line. So imagine if you're in a line at a restaurant, right? You might have A, B, and C walk in, and then A gets served, and now they're out of the line, and these people move forward, and then D shows up, and they go at the end of the line. So we can kind of have these things work, at the same time or in parallel, and the first person or the person at the head of the line is always the person who gets to be served, and the person at the end of the line or the last person to show up is always the last one to be able to go. Right, so hopefully that's pretty common sense, right? It's kind of the way that we usually do things, in personal scenarios. Now, we could always do this an opposite way, right? That might seem a little counterintuitive at first, but we'll think more about it. So let's say we show up to the deli, and there's the person working the counter, and we have the line in front of them again. And so A shows up, and then B shows up. So what we probably wouldn't do in a scenario like this, but just for the sake of an example, is whenever a new person shows up, the opposite of what we just did was say, well, okay, the person who shows up doesn't go to the end of the line, they go to the front of the line, right? So if A showed up and B showed up, they would stop taking the order of A and just, oh, B, all right. The cashier has a short attention span and just serves whoever shows up, the new person, and then gets back to working on A. So we can totally have a scenario like that where the last person to show up is the first person in line. And it maybe doesn't make a whole lot of sense to do that for something like this, but it is totally a thing we can consider, right? In this case, it would be a first in, last out kind of situation. So the first person that arrived is going to be the last person that leaves, or the last person that gets served. So if that's the case, it'd be kind of bad customer service, but A has to wait the longest, and as everybody else keeps showing up to the restaurant in front of them, they're going to have to keep waiting until all of those people have been served before they get served. Now, a more apt example for that might be stacking blocks. So imagine I have a block, let's just say block 0, and then I want to stack block 1, and then I want to stack block 2. Now, if I was to ask you to take these, Lego bricks or Jenga blocks or whatever it is, and stack them in this order, then it's a little bit harder to, put a block 0 at the top of your tower, right? Like, how does that work in Jenga? If you start with one block and you just suspend it in midair and start putting the other blocks under it, I don't think that's very possible. So if we had something like that, we might say, well, the first thing goes at the bottom, and then the next thing goes on top of that, and then the next thing goes on top of that. So we'll make it more orderly, I guess. So if I was to stack things in the way that they come in order, then I would probably end up with something like this, right? If I was to go in and put things one on top of the other. And then if we think about the way that we would remove things from this stack of things, then, if I asked you to take a block off this Jenga tower, you would have to start with this one, right? If we didn't and try to remove something in the middle or at the very bottom, then the whole tower just falls over, and, now we don't know where the blocks were, and we have a bit of an issue. Right, so this is that idea of the first thing that was in is the last thing that goes out. So the idea here is the last thing that we put in is the first thing that we're going to take off. So block 2 is the last thing you stack onto a tower, right? It's the first one that you would start removing if you wanted to safely get everything off. And so when we have a structure like this is known as a stack. And I'm sure some of you are familiar with the stack because you might have in the recursion assignment gotten a stack overflow issue, and that's where the name comes from, is it actually keeps a stack as far as our program goes. So the last thing that showed up will be the first thing that leaves, and the first thing that showed up will be the last thing that leaves. Right, so let's maybe try to think of a practical example of that, and then maybe we'll try to implement this next time. Can you think of, especially knowing that Stack Overflow part, can you think of anything that we do when we're programming where the last thing that happened is the first thing that leaves? I might want to rephrase that some way. Can you think of anything where the code executes and the last code that executed is going to be the first one that finishes? And I'll give you a hint. Your Stack Overflow specifically occurs when you use one specific type of thing in a program. There's one thing we use stacks for. Any guesses? I'm trying to be vague, but you might have some inkling. So imagine I write a program void f, void g, and then I go into int main. And we'll just, excuse me, we'll say that g, its definition, it just calls f, and that's all it does. And then f, all that does is it couts a line feed or something. You know, it does basically nothing. Now, if I was to go into main here and call this function g, then what happens in terms of my code execution? Well, it goes and it calls g, right? And if you remember, what a function does is it just jumps to where that code is located, right? So whenever I call a function, you know, it kind of just executes the code contained by that function, right? Is what a function is. So when I call g, it will go and call f. So if we think about what functions are executing, the first one we entered was main. And then the next one we entered was g. And then you'll see here, g is going to go to f, right? Which means that it's going to go and it's going to jump over here. And so once we hit that function f is being called from g, which is being called from main, right? We kind of have this list of things in that specific order. Now what you might notice is that if I was to return or think about the order that these functions are going to finish, then it's the exact opposite order in which they were called, right? If I was to think about the execution of this program, f is going to go and do its business, and once it finishes, it goes back to where it was called from, right? So in other words, f is going to be the first one that gets removed, g is going to be the next one that gets removed, and then the program ends when main ends, right? So if we use a stack structure where the first thing that we call is the first one that leaves, then that's a stack, right? So when you get a Stack Overflow, what's happening is you're calling too many functions, the stack gets too big, it can't fit anything on it anymore, and that's why it occurs, is you have too many functions, it can't fit them anymore, and it crashes your program, which I'm sure some of you have seen for the recursion example specifically, because that one has a lot of function calls. Right, so there's definitely some usage to this, even though it seems counterintuitive, right? With that deli example, to have the last person that showed up be the first one that gets served, there's some merit to that if we need to kind of backtrack or keep a history of things that we're doing. So I don't know. Maybe we'll talk about one other thing, but really quick, any questions on how these function so far? And we'll do more examples of this next time, too. We'll figure out how we actually would program this, maybe. Right, so let's just talk about one last thing with it, and then we'll call it a day. So there's a queue and there's a stack, and these are the two that we've talked about so far. We'll just do 3. I think that's good enough. And then this part is the top, and this part is the bottom, or the end of it. And then I wrote this one backwards. Right, so they have a difference in the order that they go. So the top of a stack is the most recent thing that's come in, and the bottom of a stack is the last thing, the first thing. First in, last out, first out, and then it's the opposite for a queue. And what both of these support, right, is the ability to insert things and delete things, or remove things, right? And the only difference here is the order in which they insert them and the order in which they remove them. So here, this queue, what we do for the insertion, so let's just maybe create a little table here. So we have an insert and a remove, which will just get the thing from the data structure, whatever it is. So for the queue, the word we use for that is, maybe we'll just use blue for that, is to, I hope I spelled it right, on queue. And this is just the terminology. I'll try to use it, but they're really just fancy words for insert and remove. And the word for removing it is to dequeue it. So this puts something into a queue, and this puts something out of a queue. And the insert here for a stack is to push. So that's the reason the vector class has said push back this whole time, is you're pushing things onto that vector. And a remove is a pop. Right, so maybe we'll just write the code for this really quick and then we'll call it a day. So if I made a queue here, which we'll call queue just to be confusing, then what the above structure was is that we on-queued A, and then we on-queued B, and then we on-queued C. B, and C, hopefully those are the right colors. And then with the stack above, we pushed them all, right? So if I said stack S, S dot push. And then we just did the same thing, right? To save on writing. So if I push onto a stack in the same order that I queue into a queue, on queue into a queue, then you'll notice that the order is different, right? So this here, right, was just saying this is the order that we inserted ABC. So inserting into a queue, right, puts them in order, and a stack puts them almost in reverse, really, right? Okay, I think we'll maybe say that's where we'll call it for today. So we'll talk a little bit more about this next time and maybe some of the applications of these and then how we would actually program it. Any last questions on either the exam or assignment 9 or anything that anybody has? For sure. I'll stick around for another minute or two. If you have any questions, just let me know. If not, I will see you next Monday.